In today's notes, we're going to talk a bit more about atoms and delve more into the structure of the atom. We're going to be discussing how to determine an atom's charge, its mass, how to determine how many of each of the subatomic particles it has. So before we get too far, we're going to define atoms. Atoms are the smallest indivisible part of an element that still behaves like that element. All right, so what you have in front of you underneath that is what you would see in your periodic table. The number at the top is what we refer to as the mass number. And the number at the bottom we refer to as the atomic number. If you ever forget those two things, they're actually labeled on your reference tables: atomic mass and atomic number. What they don't tell you in your periodic table is what those numbers mean. The mass number is actually the number of protons plus the number of neutrons. Those are the only particles in an atom that have any measurable mass. So when you look at the mass number, you're actually seeing the number of protons and neutrons added together. Also, it doesn't tell you, but the atomic number is the number of protons. So if you know the number of protons and you know the number of both of these put together, when you subtract the protons from this number, you will get your number of neutrons. That'll become more important when we begin talking about isotopes later on. So we discussed previously in the other notes when we talked about the history of the theory of the atom, that an atom has to have an overall net charge of 0. But we also now know that we have these subatomic particles that do have charge. So let's talk about where those charges come from. So in speaking of our gold atoms, we said that gold has 79 protons. So it has 79 protons, and protons are positive. So it has 79 pluses. We also know that it must have electrons, and electrons are negative. If it's going to have an overall charge, a net charge of 0, then it must have 79 electrons. Atoms, if we say it's an atom, always have a 0 net charge, but that's not always the case. Sometimes we have ions. Ions are atoms that are charged. In order to have a charge, the only thing that can change are the electrons. We said before that protons define the element, so the number of protons can't change, only the number of electrons. So they're charged, and they're charged due to the gain or loss of electrons. Chemists are really lazy, and they like to abbreviate a lot of things, and electrons are E- typically. So I'll probably end up using that. All right, so let's talk about an example of an ion. We have Ag plus 3. So I know this isn't an atom because it doesn't have a 0 net charge. It has a +3 charge. So it's an ion. Now, how does that all work out with our number of protons and electrons? So silver, when you look on the periodic table, you're going to find it right here. And silver has 49 protons. Or 47 protons. That's the atomic number. So for protons, we have 47. For electrons, we'll have to figure that out here in a second. They're negative. Our overall charge has to work out to be +3 or 3 plus. And the only thing that can change is our electrons. So if it has a +3 charge, that means it has 3 more pluses than it has minuses. So we must have 44 electrons. So this plus charge that we have here is actually due to the loss of 3 electrons. Sometimes it's hard for students to kind of configure. When you think of loss, you think of something becoming more negative. But because we're losing negative charges, it becomes positive. Let's look at another example. Let's say I have given you an ion, Br-. Chemists are really lazy, so a lot of times you're going to see the charge on something with just the charge and not the number. But the only way that we would ever do that is if it was a 1. So if you see a negative or a plus without a number, it's really -1 or +1. That's the only time you're not going to see us write the number. So for protons, we're going to have to look up the atomic number of bromine. Bromine, you're going to get used to this stuff, is way over here. It's in group 17. That's this row. And it has 35 protons because the atomic number is 35. So for the electrons, we know they're going to have a negative charge. And we have to end up with an overall -1 or 1 negative charge, net charge on our ion. So that means we have more negatives than we have positives. So we can't change this number, or it wouldn't be bromine anymore. We can only change this number, and it has to have 1 more negative, or 36 electrons, which is 1 more than it normally would have. If it was an atom, it would have 35 electrons. So this was a gain of 1 electron. And that's how you figure out how the subatomic particles have changed due to a charge. Now we're going to talk about isotopes a little more. Isotopes are elements of or atoms of the same element that vary due to their mass. And the only thing that can change in an element and still have it be the same element that would change the mass are the neutrons. So we're going to say it's the same element, different number of neutrons. So our number of protons is still the same. It's just our neutrons that have changed. Now, when you get a sample of an element, typically it's not all the same isotope of that element. A portion of your sample will be one mass, another portion will be another mass, and so on. Sometimes this is hard for students to understand, so I'm going to show you how to relate this to something you probably do understand, because I'm sure you all care about this, and that's your grades. So let's look at how a person might calculate your grade. So let's say these are all your scores in a class. If we just did an average of all those scores, we would just add up all of those numbers and divide by however many numbers there are. So when we do that, you end up with a total of 840. And there were 10 grades there, so your average would be an 84 average. Now, that's not how I calculate my grades, nor is it how very many of my colleagues do it. We weight your grades based on the category that they're in. So I actually take your quiz average. Let's say that your quiz average is an 85. And that is going to be 20% of your grade. And your CASEL learning average, let's say you have a 90, is 20% of your grade. Your mid-quarter test, let's say you got an 80 on that, is 30% of your grade. And your end of the quarter or quarter exam is going to also be 30% of your grade. Let's say that was a 90. So when I go to figure out your average, I actually convert my percentage to a decimal, like so. Oop, make that a little more obvious. Do the same thing here and here and here. And then I multiply those numbers. Actually, let the computer do all of this. And then I add them up in order to get your quarter average. So I'm going to do a little math here. The math there, I multiplied your average times the weight that that average got. And now we just need to sum it up, like so. And the weighted average would be an 86. Now the way that we weight the average of an isotope is very similar. So what we have here are the naturally occurring isotopes of nitrogen and their abundance in nature. So if I had a sample of nitrogen gas, typically 99.634% of it is nitrogen 14 and 0.366% of it is nitrogen 15. So I'm going to take that average and again convert that to a decimal. So that's like dividing by 100. I'm going to move that over 2. And I think it's an important thing to do to actually draw in those humps sometimes, or actually divide the number by 2, because sometimes students just leave that decimal there. They don't move it enough places. So now, just like we did up here, I have my decimal. I'm going to multiply it by its mass here, or the your category average. So I'm going to multiply that like so. And the numbers I'm going to get, I just need to add together. So for this one, I get 13.949. And this one, I get 0.0549. And then we add the two together, and we get about 14.0. And that is the weighted average of all of the naturally occurring isotopes of nitrogen. Now the units that we're going to put on this number, they vary. I've seen AMU, which stands for atomic mass units. I've seen U, which I guess is short for AMU, so it's just units. Or later in the year, you're going to see grams per mole. And we'll talk about what that means later in the year. But any of those units are perfectly acceptable. Now let's try this for silicon. Again, we're going to move our decimal 2 places to the left, or you can literally divide by 100 to get rid of that percentage. Then we're going to multiply those by our given masses. And we get 25.82, 1.35, and 0.930. And then all we got to do is add those up. And we get 28.1. And I'm going to label this AMU this time. So one thing you should do after you've completed one of these problems is ask yourself if your answer is reasonable. Sometimes students get so in the habit of just doing the math that if they plug a number in wrong, they won't notice. So make sure you look at your answer and see if it's reasonable. This is a weighted average of these three numbers. So it should definitely fall between the masses given. The other thing you can do is check and make sure that the one with the greatest abundance ends up being closest to the mass you've calculated. And it does work out that way. This was 92% of our sample, and this is really close to that mass. So my answer makes sense. I don't feel like I need to redo it. Go ahead and try this for magnesium. And again, I don't know why this keeps happening. In my handouts, there's only one S in magnesium. You should get an answer once you've moved your decimal and multiplied, moved your decimal and multiplied. You should get an answer of 24.32 AMU. Go ahead and try the last one. And you should get 39.99 AMU. When you look at the mass given in the periodic table for each of the elements, the mass is a decimal. And the reason why it's a decimal is exactly what you've just been doing. It gives the average isotopic mass of all of the naturally occurring isotopes of that element. And those are naturally occurring isotopes on this planet. We don't actually know the exact percentages in the entire universe, so we base this on our planet.